So here are some more definitions and notation for functions. So let's say we have a function from A to B. If we have an element of the first set, which we'll call little a, we write f parentheses a for the element of B assigned to A. So this is probably quite familiar. This is how you generally write functions in life that you've seen before. But just to write it down again in this case, to be explicit. And we say this element is the image of A. Under F. So if B is an element of B, so just to be clear, this is in B, but if little b can be written as f of A, then we say A, let me try to differentiate my variable A and my English word A. Say A is a preimage of B. Yeah, maybe implicitly under F. You can leave that out or put it in both cases. So notice I'm saying the image because there is always exactly one, and a preimage because there is not always one. So we have an element of A. It has exactly one image. If we have an element of B, it may have 0 or 1 or many preimages. So it's only this direction that you assign a unique thing. If you try to go the other direction, you might get nothing, you might get one thing, or you might get lots of things. So let's do some examples to see what we mean by this. Or maybe just to say real quickly before that, if you're having trouble with these words, think of it like a projector, like an overhead projector. You have, the projector is mapping things to the screen, and each point on the projector gets sent to a point on the screen, and it is the image of that point, right? That's kind of the idea, why it's called that. So let's have an example. Let's define a function from z to z, from the integers to the integers, which is multiply by 2. So we have f of 0 equals 0, f of 1 equals 2, f of 2 equals 4, and we can write even f of n equals 2n. This is our general rule. So 2 is the image of 1. You can say that's if you want. You can also say 1 is a preimage of 2. If we think about 3 in the codomain here, 3 has no preimage. Because there's no integer that you can multiply by 2 and get 3. Okay, so before we do a couple more examples of this kind of thing, here is a really good way to write down examples. So To produce a good supply of simple examples, think about functions between finite sets. Which means a function that has finitely many set that has finitely many elements. And we can draw diagrams like this. So let's say we have f from the set 0, negative 1, 0, 2, mapping to the set 0, 1, 4, defined by the rule f of x equals x squared. So we can diagram that by drawing 4 dots here for the 4 elements of our domain, and 3 dots here for the 3 elements of our codomain, and then we just draw arrows to show the assignment. So negative 1 maps to 1, 0 maps to 0, 1 maps to 1, and 2 maps to 4. This is a nice simple way of writing things down. It's very visual, and you can write down tons and tons of examples this way that will give you lots of things to deal with when you're trying to figure out if facts about maps, functions are true or false. So let me do this now, do this example. So let's say we have set A with, I guess I gave it 5 elements. Let's give it 5 elements. And we have a set B with 4 elements. And we have some assignment that looks like this. So this one is going down here. This one is going up here. And these two, yeah, just like that. So here is just some function between 2 finite sets. And if we look at this element in the codomain, this has no preimage. This guy has 2 preimages, namely this element, and this guy has, preimages, and this guy has 1 preimage, namely this element. So it's very easy to visually see what's going on. These diagrams are really nice for writing down examples. So in addition to talking about particular elements, we can also define images and preimages of subsets. So S is a subset of A, which is our, so let's say our function is from A to B, which it has always been, but I'll keep saying that. So if we have a subset of the domain, the left-hand guy, we define the image of S under F to be, we write it as F of this subset, and it is, we can use our set builder notation to say that it is the image of S for every element of S. So it's the set of images, everything in here. So it's essentially the same thing as for a single element. If you look at a single element, you push it through the map, that's your image. And if you look at a subset, you just push it through the map, and that's your image. Although it's worth noting that if you start with a single element, you'll get a single element. If you start with a subset, you might get more things, less things. You won't get more things. You might get less things. Because things could happen like this. Where is a good example? So if we look here, this subset of two elements maps to this subset with one element. That's an example. And similarly, if we have a subset of the codomain of B in this case, then the preimage is this set, all the elements of A, such that FA is in this subset. So before, it was all the elements mapping to this particular element. Now it's all the elements mapping to this particular subset. Again, it's essentially the same idea. And one particular example of this that we talk about most frequently. So let me underline my definitions here. The image of F, so F is our map. What is the image of F? Is the image of the whole domain. So this is what it means to say the image of a map. And let me just add for clarification, where do all these things live? So if we take a subset of A, and we talk about its image, this will be a subset of B. And if we talk about a subset of B and take its preimage, this will be a subset of A. And the image of F is something like this. So that's going to be in B as well. So let's take some examples of these. So consider function from the integers to the real numbers given by f of x equals x squared, and another function which I will call g, this time the real numbers to the real numbers, defined by g of x equals x squared. So here I'm giving an example of this thing that I was talking about before. These functions have the same sort of rule that assigns one element in the domain, one element in the codomain, but the domain itself is different. So these are different functions. And here's one reason that we want to consider them to be different. The image of f is the perfect squares. 0, 1, 4, 9, 16, da, da, da. On the other hand, the image of G, what is the image of G? Well, if you take a real number and you square it, that will always be either 0 or positive. And if you take a positive real number, 0, it always has a square root. So the image of G is positive real numbers, which is to say elements of R that are greater than or equal to 0. So these are different functions, and you can see that by the fact that they have different images. So that's one of the reasons that we want to consider them to be different. And similarly, if we think about the preimage of 3 under F, well, is there an integer that squares to 3? There is not, right? It's not in the image, it's missing. So this preimage is the empty set. But on this hand, the preimage of 3 under G is not empty. It has two elements, negative root 3 and root 3.